Okay, one application of this is something called stopping forces. Consider an object of mass m moving at some initial speed vi. So this guy moving at vi, that is brought to rest over some time. Right? Stopping it, bringing it to rest, requires the same impulse no matter what forces act. Because to stop it, no matter what the details are, j is always delta p, and we end at velocity of 0, and we started with this, so we must apply minus mvi impulse for it to stop. But of course, the definition of impulse is that j is f average times delta t. So it must turn out that f average is some constant over delta t, some number. That is, the longer the collision, the lower the average force. And that's worth keeping in mind. This is the principle behind things like safety restraint systems such as airbags and seatbelts. What they end up doing is extending the time during which you stop. They make it that instead of stopping in sub-milliseconds, you stop in tens of milliseconds, and therefore you reduce your velocity, the force on you by some staggering amount, by usually a factor of 60 or so, which reduces the average acceleration and does less damage to you. In general, we want to stretch out the collision so as to reduce the force. This is a little counterintuitive because you ask people, would you like a car collision that takes longer or shorter? I think most people would probably say, I want it over as fast as possible. But it turns out that is not the case. If you could have a car crash that took 2 days to happen, nobody would get hurt. It's only because they're so abrupt that they cause the kind of damage that we see. So, for instance, cars move along horizontal roads are about to be stopped when they hit a protective barrier. All the cars are the same size and shape, but they're moving at different speeds and they have different masses. The barriers are all identical and exert the same constant force. So, as always, let's highlight the important, if somewhat unusual thing, same constant force. The cars have the same size and shape, but they have different speeds and different masses. And we want to draw a blue circle around cases that take the longest and a red circle around the cases that take the least amount of time. So we're going to go back and go through this and say, well, the time is going to be the impulse over the force, the average force. And since the forces are the same, really the time is going to go with the magnitude of the impulse. So we can just go up to this and start saying, what are the magnitude of the impulse? But the impulse, remember, is delta p. So I've got a minus sign here. Well, I shouldn't have, I guess not have my sign here. We'll have my sign up here, that if we figure out what delta p is, it's minus mvi over f average. So the larger mvi, the larger the time. So then we just multiply some numbers out. We have 10 meters per second times 3,000 is 30,000 units of momentum. 20 times 1,000 is 20,000 units of momentum. Here we have 30,000 units of momentum again, and here we have 40,000 units of momentum. So clearly this is the winner, and this is the loser for longest collisions. All right, if we have a system of particles, we define the total momentum, which is also known as their system momentum, as the sum of all their individual momenta. Notice that we've got 3 curious ways of symbolizing it. Sometimes we use capital P. Sometimes we're more explicit and say P subsystem. And sometimes we just write it out as the sum of all the momenta, and that is just literally just add up all the momentum. So if we have a thing that goes like this, and this is another momentum, then the system momentum will be just their sum. So we might move this guy down here, right? Take a line parallel. This is also the original momentum. And so accidentally I got a horizontal. That wasn't important. But that would be the system momentum. Or the total momentum, which kind of reminds you why you use this for total momentum. Calling it the system momentum is a bit provocative. It's saying that that the system of particles itself possesses a momentum, which is equal to the sum of all of its individual parts. Looking forward, that system momentum will turn out to also be the system of the center of mass, the curious point that acts like it was all the mass at one place. So let's revisit the rail car from the very first bit. Consider the system as rail car plus water, specifically only the rain that will end up in the car. We'll neglect the other stuff. And focus only on the horizontal part of the momentum because the other bit is not that interesting to us right now. Let the mass of the car be capital M, and let m sub w be the mass of the water that eventually settles in the car. Our most important thing here is that the total impulse on the system is 0. Any impulse on the car from the car on the water is exactly opposite to the impulse on the water on the car due to Newton's third. In other words, the forces they exert are going to be equal and opposite. They'll be during the same amount of time, and so the J of the car on the water, which is the force of the car on the water times delta T, is minus the force of the water on the car, delta T, which is minus J of the water on the car. Right? The total system impulse would then be the sum of these two things. Something plus minus itself is 0. Throwing together some quick and dirty algebra on that. Since J, which is delta P, is 0, then PF minus PI equals 0, so PI equals PF. We started with capital M VI. We end with capital M VF, but also the water has some. So if you sort of want to think of it this way, we have rail car, and now rail car with some water in it. The rail car, of course, had initial velocity VI and has final velocity VF, but the water also has final velocity VF and carries momentum, which is what this term is. So we can solve this over and say, well, then the final velocity has to be these two things, the ratio of the initial mass to the final total mass times the initial velocity. We started with 1,000 kilograms, but we end with 1,000 kilograms plus how much we got every minute times how many minutes we are. This all total will, of course, will be 300. So this whole thing will be 1,300. At this point, I can not worry about the kilograms because they've canceled here. And so I end up with something like 10/13 of 10, which is 7.7 meters per second. And this is quick and dirty. This is maybe 5 steps of algebra, which is way easier than that Newtonian approach that we talked about in the other video was, which would be virtually undoable just for its complexity. And here it's really, really simple because we don't care what happens during the interaction, just what happened before and how it changes at the end. We'll find that's the power of the momentum method.